Alright, good afternoon, gentlemen. Apparently, I didn't record this with any sound, so that really helps. Okay, what I'm going to recommend to you, still set this up in Cornell note style, but instead, still do the title here, set up the side, but then when you put, so the first person you're going to do is Aristotle, and then his playing card may take up like this entire space. So, and you may not have to do any notes on him, but you might want to leave yourself a little space just for any additional information that you get. And then you would go on and do the same thing for Copernicus, so on and so forth. Okay. It's your responsibility to decide what you think is important, what is not important. So, this is here for you. I'll highlight some items suggesting that something is more important than others, but you need to start picking out the key information that you think is going to be important. Obviously, the things I highlight and go over multiple times. Feel free to pause, replay, rewind. Okay. So, kind of some examples before we get into the formalized notes. Pens and cannonballs. You don't have to put this down, but it's a good example to pay attention to. Okay. So, the first thing, it brings up the cannon, but the first thing, take a look up here in the corner. This pen, if it started moving by itself, you would investigate, look for what caused it to move. You'd be like, oh, who threw the pen? Or if it was just floating in space, you'd be like, is there a hand touching it? Is there a string tied to it? How is this moving? Okay. So, only living things move by themselves. This is biology. Okay? So, things that are not alive that move, we look for an answer. Alright? We look for something physics related, theoretically, to help you identify those things. So, a cannonball is in the cannon here. Alright? It's just chilling there. It's probably more like back here-ish. I'm not sure the inner workings of a cannon. But it's back there. It's hanging out. It doesn't go until the gas of gunpowder explodes, forcing the ball out. If we were in space, the ball would continue endlessly. But what you're going to find with a cannonball on Earth, gravity affects it, so it falls to the Earth. Okay? So, what keeps it moving? There's no gas moving on it. No gas. Once it leaves the cannon, nothing's actually acting on it. It's just moving through space. Well, that's the force that was applied originally. In a frictionless space, so out in space, this cannonball would go on forever in a straight line direction. Hey, dynamic equilibrium, we've heard that before. There it goes. But on Earth, it runs into something and comes to a stop, whether it be a gravitational pull that brings it down to Earth, or whether, in this case, a random wall that it hits, so on and so forth. This idea has a name. It's called inertia. Okay, so let's go back in history. This is the history portion. Aristotle's classification of motion. So, he was born in Greece. He's a Greek scientist. This is the biggest part about him. So if these were left off the card, you need to know. He defined natural versus violent motion. Natural motion is like when something is smoking, smoke naturally rises. So when rocks fall, they naturally fall to the earth. Okay, they don't fall up. Smoke doesn't go down unless it's types of smoke that he never dealt with. All right. Violent motion is something that required a force. So for in his day, it would be a horse pulling a cart. Okay, it would be you pushing your buggy and having them stumble to the side. Okay. He believed that all objects on Earth have a place that they naturally seek, all right? Or a position, a resting place that they naturally seek. He did determine, he said, all motion on Earth is linear, motions in the heavens are curved based on his studies. He said motion continues as there's only an applied force, and removing the force will stop the object. Okay, we find out this is not exactly true, but for his day, this was kind of a huge deal. It was a change from what other people believed. 200 years this lasted. It took Galileo to change it. Okay, Copernicus. He had another idea with motion. He was like, hey, I noticed through some calculations and studies of the planets and movements of the stars and things I see in the sky that, P.S., he's Polish. Should have that on the card. He was like, dude, I'm pretty sure the Earth rotates around the sun, not the other way around. Okay, this kind of made the church a little angry because he was one of the first people who said it, and he didn't have a lot of people backing him up. So the church was like, man, there's no way. The Earth is way too heavy. There's way too much to it. The Earth is the center of the universe, and the sun rotates around it. Come on, everyone should know that. He suffered serious persecution to the point that he didn't publish material until the day of his death. And then later he was proven correct. And once there was multiple pieces of evidence that lined up with his view, the church fell in line and agreed and accepted that notion as well. But he was one of the first people to say, hey, I think this is the way it's going. Okay. Galileo. He invented the concept of inertia. He didn't name it, but he invented the idea. So he's Italian. He knew experimentation was the key to things. So he blew away Aristotle's notion of motion. He was like, dude, if I release this ball, it'll reach the same point over on this side if it's in like a round, like a pie pan. I don't know what he actually did this in. But he rolled the ball from one end to the other and realized that it will stop at equal places. Okay. It will keep its momentum back and forth, especially if there's no friction. This thing will just keep going back and forth and back and forth. Remind me to show you Newton's cradle. It's the same idea, that it'll land as long as there's no air friction or regular friction, the motion will stop in the equal side and height that it started. Well, he tested this with all different designs of slopes, realizing that each time the final position is the same as the initial position on the opposing side. So he's like, okay, what if we take away friction and just roll it on a straight ground? There's no position to reach. He determined that if there was no angle, this ball would roll on forever if there was no friction. And if you guys play hockey or you've seen hockey play, you know a slap shot of the puck can go all the way down the ice and hit the other wall. If that ice went on like a river or something, it could go continuously. Ice is considered an almost frictionless or practically frictionless surface. Note, when I say that in a test, when I say it's on ice, I'm indicating that it is a frictionless surface. Don't ask me that every test. Okay. Now we got some sumo wrestlers. He started noting like a ball at rest is just going to stay there, and a ball in motion is going to continue that path if there's no friction. Okay. So, fight against sumo wrestlers. They have so much mass. And when they stay still, they have a tendency to stay that way. If they start moving, they have the momentum to continue moving. This is called inertia. Okay, quick concept check. A ball rolling on a pool table slowly comes to a stop. Stop in your notes and tell me how Aristotle would explain it, how Galileo would explain this reaction, and how would you explain this reaction. Pause the video, do that now. Okay. Now, what two main ideas of Aristotle did Galileo discredit? To review. Stop now. Write this down. Okay. Next, what is the name of the property of objects that when they maintain their states of motion? Hint, we just talked about it. Okay. Last thing we're going to quickly review. Force versus friction. Force, may the force be with you, is a push or pull. You know that. Doesn't hurt to write it down another time. Friction. Okay. Notice I'm pointing to it like you can see me point to it. Notice there's this buildup of like steam here. That's from the friction of the tires meeting the pavement before it really grasps the pavement and starts moving. Friction is the force that acts between a material. So if you rub your hands together, you feel the friction being converted into thermal energy, so a heat source. Okay. Examples. I just showed you. Rubbing your hands together. Look at the soles of your shoe. When they were new, they were not that worn down. List 2 more examples in your notes, please. Okay. Newton, the last dude. Sir Isaac Newton, you guys should have this listed. He was a mathematician and a physicist. He discovered many things, but most importantly, and what's going to consume the remainder of our semester and part of next semester, is his laws of motion. He realized, okay, there weren't cars back then, but he realized it's hard to push a dead car unless you can knock it into neutral. It's going to put a lot of effort to get that dead car rolling because it has a tendency to stay still. Okay, this one's a fun one. You're riding in the car with your brother, sister, friends, whatever. You're all in the back seat. When your parents take a sharp left, you tend to fall to the right. Okay, go backwards in the video, but this is like the roller coaster game. I'm sure many of you have played it where you like slam into your brother or your sister and you all smash into the window side, all right? Or actually I think we call it like Jello or something where you just fall to the side. That's because you were going in one direction and your body wants to continue moving in that direction when the car's turning, all right? Dislodge a ketchup bottle. Man, I should have gone to the cafeteria. When you hit the bottom or when you shake the bottle like this and hit it on the bottom, you're trying to dislodge the ketchup by moving the placement. By hitting it, the ketchup wants to stay in its place and you're hitting it to kind of force it downwards. That was a terrible explanation. Sorry. I need to go back and do that again. Headrests are placed in cars. So when you have car wrecks, your body tends to fly forward and then back. That headrest is to hold it into place to prevent whiplash. So it may be uncomfortable, but it's there for a reason. We're going to watch this video in class, but feel free to click on it if you open this PowerPoint. You can't click on it through this video. So we'll just watch it in class. Okay. And then we're also going to look at high-speed car crashes. Okay, that's where we're stopping today. Thank you for listening. Hope you got the notes. Bye.